Welcome to this short video. Today I will introduce to you Central Limit Theorem, 2012 US presidential election Obama versus McCain. There are a lot of opinion polls coming out before the official vote. But the population of the United States is so large. How is it possible to investigate everyone's wishes? Can these opinion polls be trusted? Is it possible to predict actual voting intentions? At this time you need Central Limit Theorem. Everyone knows that when there is a random sample, when its size is n, mean will be x bar, variance will be sigma square, expected value of mean will be mu. Variance will be sigma square divided by n. When n gets bigger and bigger and size gets bigger and bigger, variance of x bar will decrease. The distribution of x bar is very dependent on n. Let's look at this example now. This is standard normal distribution. Here we plot it at different times of n. Sample distribution. This picture is when n equals 20. Then n is 50. N equals 100, n equals 200. There are still times when n equals 1000. You will easily find distribution is getting closer to bell shape, more and more like a standard normal distribution. That is its population distribution. Here you will see the curve of standard normal distribution. When n becomes larger and larger, sample mean will be very close to population mean. The subtraction of the two will also get closer and closer to 0. Y is sum of random sample of size n, and W is each random sample of y. So W will be equal to x bar minus mu. Then divide by sigma, then divide by the square root n. Expected value of W will be equal to 0. Variance of W will be equal to 1. It will be the same as standard normal distribution. They all have mean 0. Variance is 1. Main theory is, when x1 plus x2 is added to xn, n has so many independent random variables. They all have the same distribution, and its mean is x bar. There follows distribution has a finite mean mu. Another finite positive variance, sigma square. Their distribution will be W equal to x bar minus mu. Then divide by sigma and then divide by the square root n. That's n. The limit of n will be infinite. If it is a general distribution, n is greater than 25 or 30, Central Limit Theorem can already be estimated very well. And when distribution is symmetric, when unimodal or continuous, it is enough that n is greater than 4 or 5, and when distribution is approximately normal, n equals 2 or 3 is enough. Let's look at the first example now. Uniform distribution, x1, x2 is a random sample, n equals 2 from u, PDF is equal to 1, when 0 is less than x is less than 1, mu is equal to 0.5, variance is equal to 1 over 12, and y will be equal to x1 plus x2. When 0 is less than y and is less than 1, the PDF will be y. When 1 is less than y less than 2, the PDF is 2y. PDF of y is just looking through the image on the right. Red wire and blue wire instead, and PDF of random sample, will be equal to normal distribution with mean, is 2 times 1 over 2, variance 2x 1 over 12, then it is replaced by curve of normal distribution on the right hand side. You can see two curve means. It's actually very close. Therefore, normal curve is a very suitable population. Then go to the second example. Chi-square distribution. Expected value of y equals n. Variance of y is equal to 2n. W is equal to yn divided by the square root 2n. The right hand side is the PDF of W. There are two pictures below. The green line represents standard normal distribution. The red line is W when n equals 50. The black line is W when n is equal to 100. You can see two pictures. Standard normal distribution. All can approximate population mean. Compare the green lines of the two graphs. The green line on the left is very close to the black line. The green line on the right is not that close to the red line. So it is proved that when n is larger, Central Limit Theorem is more able to approximate population mean. Now I will talk about how Central Limit Theorem is applied. First, in terms of general distribution, fx is equal to 3 over 2 times the square of x. Y is the sum of 15 random sample xi. If we ask for probability of y, when it is less than or equal to 1.5 and greater than or equal to minus 0.3. First we ask for the expected value of x. It is equal to 0, and variance of x is equal to 3 over 5. If we are looking for probability of y, if it is less than or equal to 1.5 and greater than or equal to minus 0.3. First we require that the expected value of x is equal to 0. Variance of x is equal to 3 over 5. Remember I mentioned it before. W is etc. yn mu. Then divide by the square root n times sigma square. So here W will be equal to y equals 0. Divide by the square root of 15 and multiply by 3 over 5. We find that W has minus 0.1 and 0.5. Then through standard normal distribution, we will find probability. It is equal to 0.2313. Now let's look at gamma distribution. Suppose there is a bus company. Operate a minibus, capable of carrying 10 passengers, from place A to place B. After the tickets go on sale, the time between ticket sale and ticket sale, its gamma distribution, alpha equals 3, theta equals 2. Time is measured in minutes. Y is sum of random samples. Alpha is 3 times 10, which equals 30. Theta is equal to 2. If we want to find if the ticket is purchased within an hour, in gamma distribution, mu equals alpha times theta, equals 3 times 2 equals 6. Variance is equal to alpha multiplied by theta raised to the power 2. Equal to 3 times 2 raised to the power of 2 is equal to 12. Because W is equal to yn times mu, just divide by the square root n, multiply by sigma square. So here, W will be equal to y10 times 6. Divide by the square root of 10, multiplying this by 212 equals y60 divided by the square root 120. Substitute when y equals 60. We find that W equals 0. Let's look at standard normal distribution again. We will calculate that probability is equal to 0.5. The first two examples both talk about probability of y. This time this example is about probability of sample mean. This is a normal distribution. N equals 25, x bar is 2000. Sample variance is equal to 500 squared divided by n equals 25. If we want to find probability of sample mean is greater than 2050, we mentioned before, W is equal to x bar mu. Divide by sigma, then divide by the square root n. So here, W is equal to x bar 2000 divided by 500 fifths. We then substitute x bar equals 2050. Just ask W to equal 0.5. Then use standard normal distribution. Then subtract this value from 1 to get the probability is equal to 0.3085. Here we will look for value of y. This distribution, mean 200 variance 80, we want the probability of y to be less than 0.2. We get y 200 divided by the square root of 80 is equal to 0.842. Y is equal to 207.5, so y must have at least 208. Talked so much about central limit theorem. Now let's respond to the question at the beginning of the film. Y is sum of random sample xi, that is voting for candidate A, and 11 is equal to 0. It's when these people choose candidate B. Y is approximately binomial distributed, and P is equal to yn divided by n. It's a sample probability for people who voted for A, because he is also approximately binomial distributed, so his mean is equal to NP. His variance is equal to NP, so Y is equal to YNP. Divide by the square root NP. It's Y mean divided by the square root n times the variance. And P bar is equal to Y times the square root NP divided by n. Add P. Then expected value of PBAR equals P. Variance is equal to the square root of P divided by n. If we want 95% of P, all within 2 standard deviation, probability P bar within P2 times the square root of P divided by n, and P2 times the square root of P divided by n. It is approximately equal to 0.954. After we exchange P bar and P, you will see that if P probability P within P bar minus 2 times the square root of P divided by n, and P bar 2 times the square root of P divided by n, approximately equal to 0.954. Interval is equal to PBAR 2 times the square root of P divided by n, and P bar 2 times the square root of P divided by n. Confidence length is equal to 6%, so we have to choose an n. That's 2 times the square root of P divided by n, less than or equal to 0.03. 0.03 is the margin of error. Because we know P bar times is less than or equal to 0.25, so 1 divided by the square root n, smaller is equal to 0.03, so n approximately 1111 are suitable. If our P population size has 100 million people, sample size is n equal to 1200. In fact, it's enough to estimate P Let's look at the United States now. As we approach the presidential election, opinion polls conducted by different agencies, their margin of error, probably 3%. What's worth paying attention to is their sample size, probably around 1,000 to 2,000 people, already able to estimate the intentions of so many people in the United States. In fact, many of them are. It is estimated that Obama can take the lead, so there is Central Limit Theorem. We no longer need to be afraid of sample size. Could it be a problem of too little? This is a reference. Thank you for watching.